Wow, welcome once again to Physics Mail. It is still a lovely program for all of us, including you that is watching the program now. Today on Physics Mail, we are on motion part 6, and here we want to look at uses of velocity time graph. Have you subscribed to our YouTube channel? If you have not done that, look for Mathematics Mail 1 on YouTube and then subscribe. And then make sure that you also follow us on Facebook at Mathematics and Science Mail. Okay, now let's get down to the business of today, which is uses of velocity time graph. Now, in the last video, we introduced the concept of velocity time graph and we explained the various regions that we have in the velocity time graph. So in this particular video, our interest will be to look at the uses of velocity time graph. Watch the last video so that you will understand what we want to do in this particular video. That's the foundation to this one. Okay, let's move. Now, the velocity time graph can be used in finding acceleration, finding deceleration, and also finding distance. So velocity time graph or speed time graph, velocity time graph can be used in one, finding acceleration, finding deceleration or retardation, and then 3, finding distance. So the question now is how can I find acceleration from velocity time graph? How can I find deceleration, and how can I find what? The distance. Okay, so we start with the first one, finding acceleration. Finding acceleration. Acceleration is the slope of a velocity time graph. So the slope of a velocity time graph is the word acceleration. So the slope of a velocity time graph is the acceleration. Is the acceleration. So the slope of a velocity time graph is the acceleration. Thus, therefore, to find acceleration, we'll find the slope of the graph. Now, anytime acceleration, any region where we have acceleration, we have 2 points. So acceleration has starting point and the end point. So if you have this, this is the starting point of acceleration and this is the end point of acceleration. So at this starting point, we have initial time and we have initial velocity. At this end point also, we have, if you come down here, you have your time. You have your time and you also have your what? Your velocity. So there are 2 points. Point 1, starting point, and the what? The end point. The end point. So point 1 and point 2. So how do we get acceleration? Just by taking the slope. So we can now say the acceleration is given by A equals V2 minus V1 all upon T2 minus T1. V2 minus V1 all upon T2 minus T1. So let's define the terms. Where T1 is time at the initial or starting point of the acceleration. T2 is the time at the final or end point of the acceleration. V1 is the initial the velocity at the starting point of acceleration, and V2 is velocity at the end point, end or final point, end or final point of the acceleration. So we know to get time, we look at the horizontal axis. So from every point, move to the horizontal axis to get time. Let's use a graph to explain what I mean by this. If I have this v meter per second and time in seconds. If I have this is the origin, that's 0. If you have this and you have this. Now this is point 2, this is point 1. This is the starting point of the acceleration, started here and the final point is here. So what is the velocity at the starting point? Move to the vertical axis, because velocity is on the vertical axis. So from that starting point, move to the vertical axis. You notice is 0. What is the time at the what? At the starting point. From that same point, move to the horizontal axis, because time is located on the horizontal axis. So here, if you move here, the time is 0. When you come here, what is the velocity at this final point? The second velocity now. From that point, move toward the velocity axis. Whatever velocity you have here is the velocity as the final point. What is the time at the final point? From here, come down. The time you get here is the time at the final point. So you must understand these points. At this point, if I'm looking for velocity, it means I need to move from the point to the velocity axis. Then I can get velocity. If I'm looking for time, from that point I move to the what? To the time axis to know what the time is. So from a point, get your what? Velocity. Even here, this is a point. What's the velocity at this point? I need to move from here to this point. I will get my velocity. If I want to get my time from here, I will come down to this place to know the what? To know the time. You see that? So just understand this point. So at this point I have first time, first velocity. At this point I have second time, second velocity. So the starting velocity, the starting time. The final velocity, the final time at this point. So when you know these coordinates, you substitute them in the slope, then you can actually get your what? Get your acceleration. Okay? That's finding acceleration. Okay? Finding acceleration. Oh wow, not supposed to claim this. Let me rewrite that. Wow, I was thinking that I'm not using this. So where our T1 is the starting, the time at the starting or initial point of the acceleration. Then T2 is the time at the final or end point of the acceleration. Then V1 is the velocity at the starting point of the acceleration. Then V2 is velocity at the final point of the acceleration. So you must know those points like I've explained. Make sure you know the points. Very, very important. Very, very important. Okay, now let's find deceleration. Let's find deceleration. Number 2, finding deceleration. Deceleration is the negative slope. Slope in a velocity time graph. So if you go to the point where we have deceleration is the negative slope. The deceleration is given by A equals minus bracket V2 minus V1 all upon T2 minus T1. That's the negative. You see, it's different from this one now. This is the positive slope, which is the main slope of a velocity time graph. Then this is negative of the acceleration. So the same thing is applicable in terms of locating the point. I've defined these terms, so they stand. So in this case now, the T1 in this case now becomes the starting point, the starting time of the word of the deceleration. So if I use a diagram to explain these points, we know that we have this T in seconds, V meter per second. Okay, so we have this. Let's say I have this. Okay, now this is point 1 for what? Deceleration, and this place is point 2 for this, because deceleration started here, continued to this point. Acceleration started here. So here is point 1 of acceleration, point 2 of acceleration. Point 1 of deceleration, point 2 of deceleration. That means the time here now will be the first time, the initial time for deceleration, because this is the point 1. Come down here, you get the time for deceleration, where deceleration started. Look at the time where it started. What is the velocity at that point? This is the point. 3 seats to the wall, to the vertical axis. You get the velocity at the starting point. Now to get the time here, this is the point 2. Move like this. Whatsoever time that is here now, here, because this is the time axis. So you move. Whatsoever time that is here is the time at the end point of deceleration. Now how do you get the velocity? This is the point. From that point, move till you get the velocity axis. Get to the velocity and move. Whatever velocity that is here, which is actually 0, that's the velocity at point 2. If maybe we have this, if maybe I have something like this, body accelerated, then decelerated a little before, and I want to find deceleration at this region. You know, we have deceleration here, we also have here. But let's say I want to find deceleration, the first deceleration here. This is the starting point and this is the end point. So what is the time at the starting point? Come down to this place, that will give you the time. And what is the velocity at this starting point? Move like this, you get the velocity. Now, this is the second point. What's the time at this second point? Come down to this place, you get the what? You get the time. What's the velocity from that second point? Move until you get to the velocity axis, you get the velocity. The same thing here. This is the starting point for this one. This is the end point. So what is the velocity at the starting point? From here, move, get the velocity. What's the time? From here, come down, get the time. What's the end time now? From here, move, get the time down here. That's the time axis, on the time axis. Then from here, move straight, get the velocity on the velocity axis. So that's how to get your points in finding what? In finding deceleration. Finding these points, knowing how to trace these points is very, very important. Okay, let's look at the last one, which is finding what? Distance. The distance covered in a velocity time graph is equal to the area under the graph or curve, as the case may be. So the total distance covered is the area under the graph, the distance covered. So when you find area under the graph, you find the distance. So this implies that we must know the shape of the area under the graph or under a particular region of the graph to enable us find the distance. So this implies that we must know the shape of the area under the graph, shape of the area under the graph, or shape of the area under the graph to enable us know the geometrical formula to use. So you must know the area. Must know the area. Is it a shape? Is it a triangle? Is it a rectangle? Is it a trapezium, and so on? We must know. So the common areas or the common shapes are triangle, rectangle, and trapezium. Therefore, the areas of these shapes are given below. 1. Area of a triangle is half base times height. Area of a rectangle is length times width. Area of a trapezium is half x plus y times h. So we still define the terms, what they represent. We still define the terms, what do they represent. So let's quickly define them. Where B is base of the triangle, h is height of the triangle, or then L length of the rectangle, W is width of the rectangle, then X and Y opposite parallel sides of a trapezium, then h is height of the trapezium, or the distance between the two parallel sides. Okay. So if you don't know the shape that is under the graph, you will not be able to calculate distance. Let's take, for example, I have this. I have that, to that, to that. No, that's that, to that. Velocity meter per second. and time in seconds. Now if someone say find the total distance covered, so that's the total area, and you know this shape is what? A trapezium. So if I want to find the total distance covered, I will be finding the area of a trapezium. That means I will use this formula, which is area of a trapezium, to find the total distance covered. You see that? So if you don't know the shape, you will not be able to actually carry out the calculation. For example, if they now say, what is the distance covered during acceleration? Now look at acceleration from here to here. This is where acceleration, it started here, and that's the end. So what's this distance covered during acceleration? The shape of acceleration during acceleration is a triangle. So if I want to get the distance covered during acceleration, I will be calculating area of a triangle. So I will be using this formula to find the area of a triangle, where from here now to here is the base of the triangle, and from here to here, which is from here to here, is the height of the triangle. The same thing, distance covered during deceleration. Look at deceleration. Deceleration is here. It started here, and that's the end. So deceleration is also a triangle. So if I'm looking for distance covered during deceleration alone, I will be finding area of a triangle. That's the formula I will still be using. But if they say, what's the distance covered during uniform velocity? Uniform velocity, that's the beginning and that's the end. So you see the shape, look at it, is what? A rectangle. So I will use area of a rectangle to determine the distance covered during what? During uniform velocity. So you must know the shape of the figure, so of the shape of the area under the graph. Very important. Let me add this in case. Okay, let me leave this here. Please note this. All these things you see, B, H, L, W, X and Y and capital H, do you see that we can either get them from time or velocity axis? For example, if you talk about half base times height, this is the base of this triangle, and this is the what? The height of this triangle. Now, from here to here is actually dealing with time. So it means that this B actually represents time. It represents time. This B is time. Why this H is vertical? So it can be obtained from the vertical axis, right? That means this H is a velocity time, because from here to here is from here to here. You can measure it on the vertical axis. The ones that are horizontal here are on the time axis. So it means that this H is actually what? It's actually a velocity. Why this B, base, is along the time axis. So it's what? It's time. So B is time in this case now. H is what? H is velocity. Now if you say length times width, if you are dealing with this, you see that this length is also horizontal. From here to here is from here to here. So this length is along horizontal. So it's talking about time also. Why this is vertical, it can be obtained from the vertical axis. This is horizontal, obtained from the horizontal axis. So you see the length now in this case will represent time. The width is the velocity. So note the terms B, H, L, W, X, Y, and H represent either time or what? Velocity. Since they can be obtained from the velocity or time axis. Very important, very important. Wow, that's nice, that's nice. So these are the things we need to know in order to carry out calculations in accelerated motion using what? Graph. That's the graphical solution. That's the graphical solution to accelerated motion. Okay. The next class, we are going to look at some examples on accelerated motion. That's graphical solution to accelerated motion. We're going to pick one or two graphs and then solve problems on that to actually drive home everything we have said in this video. Thank you for watching us till now. Till I come your way next time, continue to visit our platform and enjoy a lot of meals that are there for you. They are all for you and you alone. I love you.